Okay, so today we will discuss about the momentum transport in the fluid flow inside an annulus. Okay, so yesterday you already discussed about the fluid flow inside a pipe with Bu Winnie, and today we will continue the discussion. Okay, so today we'll have annulus. Okay, so annulus basically is like this. So annulus basically is a pipe inside a pipe. Okay, so you have small pipe inside a bigger pipe, but both of pipe is concentric. Yeah, what is concentric? Concentric means they have the same center. Okay, they have the same center here. Okay, so this is annulus, and uh, inside this annulus we will have a Newtonian fluid flow from here upwards. Yeah, so the flow is upwards, and we will have Newtonian fluid. Why we have Newtonian fluid? Because if we have non-Newtonian fluid, the viscosity is not constant. That will be very difficult. Okay, and the flow is laminar. Yeah, the flow is laminar also to make everything easier, and the flow is incompressible. Okay, so from Newtonian we know that the mu is constant. Incompressible, we know the density is constant. Yeah, and the flow is upwards. Okay, so to solve or to know how is the momentum flux distribution, yeah, to know how is the momentum flux distribution, we have to make a shell momentum balance in this case. Okay, so to make shell momentum balance, the first thing that we have to do is draw the shell. Yeah, draw the shell. So how is the shell? I will try to draw it here. Hopefully it's clear enough. Now I have the cross section of our annulus. Okay, so this is the cross section. Okay, so this is the small pipe and this is the bigger pipe. Okay, so this is the cross section of the annulus. To make the shell balance, firstly we have to make the or we have to determine the control volume. Okay, so control volume is a thin parts of the fluid flow that looks like this. So this is our control volume. Okay, so that is our control volume. And just like yesterday, we have two components of flux momentum. The first one, we have V RZ, and the second one, we have V ZZ. Okay, so now we have to draw. Oh, sorry. Before that, we have to determine what is the 0 point coordinate. Yeah, because the flow is upwards, so I will choose this as the zero point coordinate. To this directions it's Z, and to this directions is R. Okay, so this is the 0 point, Z and R. Okay, now we have VRZ and VZZ. Okay, now we have to draw where is the VRZ in, where is the VRZ out. what is the phi zz in and what is the phi zz out. Okay, phi rz means that the flux momentum is to the r directions. Okay, so basically we can draw like this. This is the phi rz in at r. Okay, and this is the phi rz out. Okay, the phi rz out at r plus delta r. Okay, now next is phi zz. Okay, phi zz is the flux momentum to the z directions. Okay, so basically that will be in line with the direction of the flow. Yeah, so here I have the phi zz in at z equal to 0. Yeah, at 0 point. Okay, and phi zz out at z equal to L. Okay, because the length of this pipe is L. Okay, clear enough? I think so, yeah. Do I miss something? I think so, yeah. I miss something. I miss the dimension of the pipe. Okay, so the radius of the inside pipe of the small pipe is kappa r, kappa capital R, and the radius of the big pipe is R, capital R. Yeah, not because we have two pipes, so we have two radius. Okay, here the radius is kappa R, and here to the bigger pipe, the radius is capital R. Okay, now we can construct the shell momentum balance here. So basically momentum balance say that momentum in minus momentum out plus or minus, yeah, plus the external force equal to 0 at steady state. Yeah, what we have here is the steady state condition. Okay, now what is the momentum in? For the momentum in, we have phi rz at r, yeah, at r, and please don't forget that this is the flux momentum. Flux. What we want to have here is the momentum, the rate of momentum, yeah, the rate of momentum. So what we want to have here is the rate, not the flux. So to have the rate from the flux, we have to multiply the flux by the cross-sectional area, yeah, or by the area perpendicular to the directions of the flux. So because we have phi rz and the flux move towards these directions, so the area that's perpendicular to phi rz is 2 phi r L. Yeah, so basically that's the selimut tabung. Yeah, 2 phi r L. Okay, that's in. And we also have momentum out rz at r plus delta r 2 phi r L as well. Okay, so that's for phi rz. Now we have another flux momentum phi zz at 0 in, yeah, in at 0 times the perpendicular surface. Yeah, this is similar to yesterday. So the perpendicular surface is 2 phi r delta r, yes, and out at z equal to L, and the area is 2 phi r delta r as well. Okay, so I hope you still remember or you understand why do we have 2 phi r delta r here as the perpendicular surface to the phi zz. Yeah, if you forget or maybe still confused, you can ask me. Okay, and now external force. Okay, so for the external force we have gravity. So basically external force we have gravity. We have rho g times the control volume, yeah, the control volume of our shell, yeah. So basically the control volume is 2VR delta R times L, similar to yesterday, exactly the same, equal to Z. Now we have to look closely at the sign of the gravity, okay. We know that gravity force is downwards. The direction of the gravity force is downwards, while now we have upwards flow. So that means the gravity put minus in front of the gravity, yeah, because the direction of the flow is in opposite with the direction of the gravity force, yeah. So yesterday, if you discuss about downwards flow, the gravity will be positive. But today, because we discuss about upwards flow, the gravity here will have negative sign, okay. Divide everything by 2V delta RL, we got VRZ at R times R minus VRZ at R plus delta R times R, divide by delta R plus VZZ R, VZZ at 0R minus VZZ at L times R divided by L minus rho G R equal to 0. Yeah. Questions? Okay, please. Aimi, please.
I forgot how to get the cross-sectional area for the PZZ.
Okay, so how to get the 2VR delta R as the cross-sectional area here? Yeah. So basically, if you look at this graph, at this figure, the VZZ momentum moves like this. Yeah. So basically, the cross-sectional area or the area perpendicular to the VZZ flow is this area, right? Basically, the area that is perpendicular is this area. Yeah. Also the same at the bottom, but I cannot draw it. Yeah. So I draw it here. Okay. So this area. So basically, that area, yeah, I draw it a bit thick here, but actually this area is very thin. Yeah, the thickness of this area is just delta L. Yeah, the thickness is just delta L, and delta L is extremely small. Okay, I draw it thick just to make everything clear. So how to get that surface area? So if I can show you this, yeah, so this is our shell, and let's make this as our shell. Yeah, so the shape is cylinder. Yeah, the shape is cylinder. So the perpendicular area to the VZZ is actually this area. Yeah, actually this area. How to get this, how to determine this area? Yeah, so to determine this area, I can just, because it's very thin, if I cut this paper, if I cut this cylinder, yeah, if I cut this very thin cylinder, cut it, I can open it like this. Yeah, so basically, from the cylinder shape, from this circle, we can cut it open, and because it's very thin, it will become a very thin rectangular. Yeah, so from here, this area, and then cut it open. Basically, this area can be lay flat like this and become a very thin rectangular. Yeah, so basically this area, the red one, if I cut the cylinder, if I cut the shell, can be drawn like this. Yeah, imagine this rectangular is very thin, yeah, just as thin as this. Okay, just imagine. So what is the thickness? Yeah, what is the thickness of this rectangular? Yeah, so cylinder, cut it open, become a rectangular. The thickness of this rectangular is delta L. Yeah, exactly the same as the thickness of our shell. Yeah, and then what is the length? The length of this rectangular, because it came from a circle, the length of the rectangular will be similar with the what is keliling? Yeah, keliling of the circle. Yeah, so now for the length of the rectangular, we can put 2pr. Yeah, okay. So this comes from the keliling of the circle. I forget what is keliling. Okay. So that's why we can have 2VR delta R as the perpendicular area to the VZZ, okay? Is that clear enough? Okay, thank you. So I can continue, yeah? I really hope we can finish everything in 50 minutes, but if we cannot, and if you don't have any other classes, we can extend a bit, yeah? Okay, so now I have this. I have this, okay? So I can move this part to the right. Yeah, I can move this part, the VRZ part to the right. And what I will get is VZZ at 0 R minus VZZ at L R divided by L minus rho GR equal to, yeah, because this part is moves there, the one with negative sign will be positive and the one with positive sign will be negative. Yeah, so it's will be opposite sign. So I can write VRZ at R plus delta R minus VRZ at R times R divided by delta R. Okay? This is differential form. Okay? So I can write dou VRZ times R. Yes, we still have R here. Divide by dou R equal to VZZ at 0 minus VZZ at L, okay, minus rho G, and put the radius, all the R outside the bracket, and then divide by, divide by L like this. Okay? Yep. And then from this equation, we have VZZ and VRZ. As we know that the flux momentum consists of the momentum of the convective flux and the molecular flux. Okay, so for the VRZ we have rho VR VZ plus pressure Kronecker delta RZ times plus the tau RZ. And for the VZZ we have rho VZ plus pressure Kronecker delta ZZ plus tau ZZ. Okay, let's have a look here. VR, we don't have the velocity to the radius directions, yeah, so we only have velocity of the fluid to the z directions, yeah, because we have only laminar flow, so nothing moves to the I directions. So VR is 0. Now Kronecker delta RZ, remember Kronecker delta R is not equal to Z, so this part is 0 as well, yeah. Now for the VZZ, let's have a look here. We have rho VZ, yeah, we have that. And Kronecker delta ZZ, yes, Kronecker delta ZZ is actually equal to 1. So what we will have here is just the pressure, and then tau ZZ. Tau ZZ is basically minus mu dou VZ per dou Z, yeah. We don't have any velocity gradient to the Z direction, so that means this part is 0 and tau ZZ is 0 as well. Okay, so at the end, we only have tau RZ, rho VZ, and pressure for the Z. Okay, now if I take this part, only this part, if I take this part, yeah, the one on the red rectangular, and then I make a little note for that part, yeah. So that's VZZ in minus VZZ out, yeah. Basically that's VZZ in minus VZZ out. Now we can substitute the VZZ in with rho VZ, okay, plus pressure at 0 in is at 0, yeah, at 0 point, minus rho VZ out plus pressure out. Pressure out is at Z equal to L. So I put P pressure L here as a symbol, okay? So if we look at this, we know that at the inlet and at the outlet, the velocity will always the same, yeah. So basically, this part and this part is cancelled out, yeah. So from the flux momentum ZZ, we only have P0 minus PL. Yeah, so the pressure at 0 minus the pressure at L. Yeah, I think Bu Winnie already explained this to you yesterday, that P here is the pressure of the fluid. Yeah, it's the pressure of the fluid, it's the pressure of the flow. So I can put this back here, and I will have R in the bracket P0 minus PL, L divided by L, minus rho G, okay, equal to dou VRZ times R divided by dou R. Okay, now it's a bit of trick, just like yesterday. We can change this equation into P0 minus PL, and I want also to put rho G up here. So it's plus rho GL, divide everything by L. So rho GL divided by L actually is rho G. So we have this, and I want to make the same exactly similar equations over here. So I can write plus, we have plus rho G 0, yeah, rho G times 0, yeah. So basically, because this one is at our 0 point, the rho G 0 will have no value, yeah, it have no value. It's just being put here to make this and this similar, okay, equal to dou VRZ times R dou R. Yeah, so now we can do the first integrations. We can do the first integrations, dou R here. So we will have, oh sorry, I forget, yeah, before that. So you already know that this is what we call as the modified pressure. Yeah, so this is what we call as the modified pressure. So if you compare this to the yesterday's example, you will find that the modified pressure is a bit different. Yeah, so yesterday you have the modified pressure as P minus rho GL, P minus rho G0, yeah. But today your modified pressure is P plus rho G0, P plus rho GL, yeah. How come it become different? Yeah, because you know you cannot try to remember everything in transport phenomena. You have to understand the phenomena, okay? So because the flow direction is different, so this sign is also different. Yeah, please note that. Okay. Until now, any questions? Any question? If you have questions, uh, write questions in the chat. I think. All good? Okay, all good. Continue. So we can do the first differentiation, the first integration of this equation, and then we will get that questions. Okay, okay, Fauzan, please ask your questions now.
Okay, Miss. Sorry, Miss, but I still don't understand how can we get rho G0.
So basically, the rho is zero here. Rho is zero. The value is zero actually. Yeah, it has no physical meaning. It's zero. But why we put it here? We put it here just to just to make a similar equation like this. So we want to have pressure plus hydrostatic, and we also want to have pressure plus hydrostatic. Yeah, even though actually the hydrostatic at the 0 point is zero actually. Yeah, so do you understand what is the difference between pressure, hydrostatic pressure, and modified pressure? Yeah, so that's what I want to ask you first. Not only Fauzan, but everyone in the class. Yeah. So do you know what is the difference between pressure, hydrostatic pressure, and modified pressure? Why do we have a lot of pressure here? Any idea? If you have idea, write it in the chat, and if you have no idea, just write it in the chat. Yeah. So I know. Okay. Okay. Because I cannot hear you properly because when I speak. Yeah. Okay. So don't know. Okay. Illustration, yeah, a bit of illustration. So basically what we know as the pressure here, yeah, symbol P, just the regular P, this is the fluid pressure. Yeah, what we have as the rho G L or rho G 0 or everything, yeah, even though rho G 0 is 0, this is the hydrostatic. Yeah, and what we have as the modified pressure, the strange P, is actually the total pressure. If you still remember from your fluid mechanic, the total pressure of your fluid is not only exerted by the fluid itself, but also depends on the hydrostatic based on the level of the fluid. Yeah. So if you still remember, you have Bernoulli equations. That's P plus rho GH plus rho VV plus not rho VV, yeah. Sorry. You have half rho V square and then equal to something. Yeah, this is Bernoulli. So basically this is the pressure of your fluid, this is the hydrostatic of your fluid, and we don't have this because we always, so actually this part, the mechanical part, the kinetic part has a value, but just like we discussed it before, our yesterday, should be yesterday. Yeah, the velocity in and the velocity out is the same, so we don't really look at this part. Yeah. So what we know as modified pressures is the addition of your fluid pressure and the hydrostatic pressure. Okay. So now, for example, it will be easier to have illustration if I draw a horizontal pipe here. Okay. If we have horizontal pipe and we have fluid flow to that directions, yeah, and then out here, okay, do you think there will be a difference between hydrostatic in and hydrostatic pressure out? Okay, do you think there is a difference between hydrostatic pressure in and hydrostatic pressure out? Maybe you should write it in the chat, yeah, so I can read it. Any idea? No, yeah, yeah. Good, yeah. There is no difference in the hydrostatic pressure, yeah, because the level is the same. So that means rho g times maybe h in, yeah, will be the same as rho g h out. Yeah, that will be the same. Now, even if there is no hydrostatic pressure difference, when the fluid flow like this, what is the pressure here and the pressure here? Pressure in and pressure out. Will it be the same? Will it be the same? The pressure in, the fluid pressure in and the fluid pressure out, will it be the same? No. Yes. Yes. The fluid pressure in and fluid pressure out will not be the same. Okay. So this is what we know as pressure, P. P out, the regular P. Okay. Yeah, so the pressure in will not be will be different with pressure out. Why? Because we have friction here. We have energy loss due to the frictions. Yeah, so that's why our pressure in, pressure out will be different. Yeah, so here the pressure in plus rho gh in, this is the modified pressure in. Pressure out and the rho gh out, this is actually the modified pressure out. Okay. Yeah, so this is the modified pressure, this is the fluid pressure and the hydrostatic pressure. Do you get the difference? I hope you get the difference. Yeah, so pressure, these pressures is something that can be related with the, if you still remember, yeah, but I think you still remember the finding friction factor, friction loss and things. This one is hydrostatic and the modified pressure is the combination of both. Yeah, the summation of both. Very clear. Okay, thank you. Now, one more example, yeah. So, do you still remember in our first meeting, we have falling film. Yeah, we have falling film. We have falling film. We have falling film like this. Yeah. So, you remember that at this case, we say that pressure in and pressure out is equal. Yeah, so pressure in equal to pressure out. Why was it equal? Because the system is open to atmosphere. Yeah, when the system is open to atmosphere, it cannot retain, or it cannot retain more energy. And even if it lost energy because of the frictions, the atmospheric pressure will give it extra energy. So basically, no matter how severe the friction here, the pressure in will always 1 atmosphere and the pressure out will always 1 atmosphere as well, because they have the help of atmosphere to maintain pressure no matter how severe the friction happen during the flow. Okay, so in this case, yeah, in this case, the pressure in equal to pressure out. What will make the total pressure difference is just the hydrostatic. Yeah, that's why in this case you have rho g cos beta something at the end. Yeah, this stands for the hydrostatic pressure difference. Yeah, but for the fluid, for the fluid fraction different, for the fluid flow difference, you will not have the difference in that pressure for the fluid flow. Okay, I hope that's clear enough. Okay, so the fluid pressure difference only happen in a closed system, and if there is a flow. Yeah, if you have closed system and you have fluid, but the fluid is not flowing, means that there will be no friction, so you will not have the difference in the fluid pressure. Yeah, so you have to look closely at each of the phenomena. Yeah, I will not recommend you to remember everything, because that will make life very hard. Okay, yeah, just understand. Clear? Okay, yeah, I hope that's clear. So basically, the rho g zero here has no value. Yeah, I just want to put it here to show that modified pressure consists of the fluid pressure and the hydrostatic pressure. Yeah, even though at this part, the hydrostatic pressure at the bottom of the pipe must be 0. Yeah, because it's in the bottom. Yeah, the one that have a value is the rho gl, because it's like over here. Yeah, the one at the bottom, 0. No hydrostatic pressure relative to this one. Okay, I hope that's clear. What should we do now? Oh, okay, here. So we do one integration over here. So what we will have is modified pressure 0, modified pressure L, divided by L, R dr. I will have r square and 2 here. Yeah, plus c plus c1. This will be equal to, look at this, we have vrz here, and we know that the vrz component is just tau rz, the others is 0. So I can just write dou tau rz divided by dou r. Okay? No dou r. We already do integration on this. I forget. It's just tau rz. Now to solve this problem, we have to choose one boundary condition. Okay, one boundary conditions. Because this is tau rz as a function of r, so the boundary conditions must be at r equal to something, tau rz equal to something. Yeah. Oh, very good timing. You come again. Now, okay, let's see. For this case, yeah, or maybe this one is too messy, use this one. Yeah, I will make a big change over here. Oh yeah, okay. So do you have any idea at which r we know the value of tau rz? Yeah, so basically tau rz is minus mu dvz per dr. Okay, thank you. Yeah, thank you. Always forget this since yesterday. Forget the r since yesterday. I don't know why. Yeah. So this part should be times the r. Sorry. Then if I divide everything by r, I will have P0 minus PL divided by 2L times R plus C1 divided by R equal to tau RZ. Okay, yeah. So the boundary condition at R equal to something, the tau RZ equal to something. Yeah. So we know that the tau RZ is minus mu dvz over dr. Yeah, so if we look at the velocity profile. Yeah, we have upwards motions, we have upward flow, and the velocity profile will basically looks like this. Yeah, it won't give you a perfect parabolic and symmetrical parabolic like the flow in the pipe, like just in the pipe yesterday. But it will give you something more or less like this. Okay, but what is symmetrical is these shapes will be symmetrical with the one here. So I can draw it like this. Okay, yeah. So just as if you put a mirror in here, yeah, the shape will be symmetrical, but the shape itself is not the perfect parabolic like maybe like my drawing is not that good, yeah. But basically the shape is not the perfect parabolic like this. Maybe it's a bit skewed to the right or a bit skewed to the left, yeah, but the shape here will be symmetrical with the shape over here. So that's the velocity profile. We know that at the maximum velocity, yeah, at the maximum velocity, this is the extreme value, the extreme point. At this point, the dvz over dr must be 0. Yeah, that's the maximum point, minimum point, just like the one we have in calculus. So at this point, dvz per dx as dvz per dr will be 0. Means that at some radius, the tau rz will be equal to 0. Yeah, because dvz per dr is 0. Okay? The question is at which r? Yeah, we don't know exactly at which r. You just say this is lambda r. Just say this is lambda r. So at r equal to lambda r, yeah, the tau rz equal to 0. So put everything here. We have modified pressure 0, modified pressure L divided by 2L R. Oh, change it into lambda R. Lambda R plus C1 lambda R equal to 0. Yeah, means that will give us C1 equal to minus modified pressure divided by 2L lambda square R square. Yeah, I think so. Yeah. And then, so the final equations for the tau Rz is modified pressure 0 minus modified pressure L divided by 2L times R plus actually that will give us minus because the constant one is minus modified pressure 0 minus modified pressure L divided by 2L lambda square R square divided by R. Yeah, that's divided by R. Okay. Yeah, so that's our equations actually, but things in the book, Bird Stewart book, they make a bit of modification to make it the equation a bit more neat. Okay, so they have tau Rz as modified pressure difference times 2L. Okay, then they usually like to put the R square here. Okay, then let me have a look to make it quicker. Okay, so to make the equation similar with the bird, just write it like this. We have R divided by r, okay, minus lambda square capital R divided by R. Okay, so basically the same equations, just different form. Yeah, nothing changed. Exactly the same. Okay, from this you can continue work to derive or to determine the velocity gradient. Sorry, the velocity profile. The velocity profile of your flow. Yeah, if you have the velocity profile equations for your flow, you can draw the distribution of the velocity. Yeah, you can know that if the whether the velocity gradient is skewed to the right or skewed to the left, or I don't know, like I don't know how. Okay, so basically just replace the tau rz with minus mu dvz over dr. Yeah, and write the rest divided by 2l r divided by r minus lambda square, the capital R divided by r. Yeah, and then you move the minus mu over here. That will give you minus here and mu here. Okay, or maybe put it to mu l. Okay, and then you need to do one more integrations. Yeah, if you do one more integration, maybe you can try to do the integration by yourself. Yeah, it's not difficult. Just do one more integrations. One more integration, you will have Vz, yeah, as a function of r, yeah, plus constant 2. Yeah, just like yesterday, plus constant 2. But please remember that you still have another constant here. Yeah, you have another constant here. Maybe you don't realize. But lambda here is a constant. Yeah, lambda r. Lambda is a value that we choose randomly, and that's a constant. So basically, in the velocity profile equation, you have two constants. You have lambda and you have constant 2. Okay? In that way, you will need two boundary conditions to solve these equations and to determine or to state what is the constant. Okay? So the first boundary conditions at r equal to something, velocity equal to something. Yeah. This is easy because here you can see, yeah, to get two boundary conditions in regards to the velocity, you can look at these conditions, yeah, and here. So I can write at r equal to capital R, the velocity is 0. Here, the velocity of the fluid is 0. And next, at r equal to kappa r, the velocity is 0 as well. Yeah, 0 as well. You can solve this equation. I think that's pretty easy. Yeah, pretty easy. You can solve this equation and you will get the velocity profile as a function of r. Yeah, and then finish. After that, you can try to determine where is or what is the maximum velocity equations, what is the average velocity equations, just like what you get yesterday, I think. And what is the mass flow rate? Yeah, and the last one, and I want to explain it a bit, so that's why I a bit hurry over here, is the one that is a bit different. Okay, so yesterday after you derive this equation, I believe you also derived the force exerted by the fluid on the wall. Yeah, the force. Yeah, now if we look at our case here, I need to erase some of the notes. Okay, so if I want to know what is the force, yeah, on the wall of the annulus, I will have two surfaces to be observed. The first one is the surface of the small cylinder, and the second one is the surface of the big cylinder. So the force acting on the surface will be the summation of the force in the inner cylinder and the force on the outer cylinder. So basically I will have two force, yeah. Force divided by surface is the shear stress, yeah. So because the fluid flows like this, the force acting, sorry, I lost my microphone. Okay, so because the fluid flows like this, the force that I will have is not the pressure force, but shear force. Yeah, shear force. So here, tau RZ. Yeah. Okay. Yeah. So now, if I want to know the total force, I will have a look at the surface. The first one is the small surface. The smaller cylinder surface is 2p kappa R times L. Ya, basically that's selimut tabung. Ya, selimut tabung kecil, the small tabung ya, the small cylinder. Times the tau RZ at kappa R. Plus for the one at the big cylinder, 2V R L times the tau RZ at R. Okay? Now, okay, this is the difference between this case and yesterday's case. We know that the value of tau, the value of the shear force, depends on the velocity gradient. Okay? At the maximum velocity, basically the shear force, the shear stress, the tau, yeah, this is for the tau, yeah, too small. So basically, at the maximum velocity, tau is 0, yeah, tau is 0. Why tau is 0? Because dvz per dr is 0, maximum point, yeah. So at this point, the tau is 0. Okay. Now, if I take just this part of the velocity profile, okay, I can have, maybe erase it a bit. Okay, I will have something like this. This is z directions, yeah, this is r directions, yeah, just like what we have earlier. Okay, now if we have a look at the profile, yeah, to make it easier, I just choose 2 points, yeah. Say that I choose these points over here and make it point 1, and I choose another point over here and make it point 2. Yeah, dvz over dr is actually v1 minus v2 divided by r1 minus r2. Okay, now let's see. Yeah, the velocity at point 1, so this one, the velocity at point 1 minus the velocity at point 2. Velocity at point 1 is higher than velocity at point 2. Yeah, so it will give me positive value. Now look at the r, at the radius. Yeah, radius 1 minus radius 2. Radius 1 is smaller than radius 2. Correct? Yeah, means that what I will have here is minus R1 minus R2 is minus, the value is minus. Okay, so basically the dvz over dr that I have is minus. Okay, is minus. Now, if I now closely look at this part, another side, I will have okay, this is Z, this is R. Yeah, so basically you can do something like that, or you can just guess. Okay, the shape is like this, means that dvz over dr is positive. Yeah, the gradient is positive. Yeah, so we will have two different gradient over here and over here, two different gradient. Okay, now if I put, to remember, tau rz is minus mu dvz over dr. Okay, so for this part, yeah, the small part over here, the dvz over dr give me positive, means that the tau rz is negative. Yeah, negative times positive will be negative. And over here, for this one, the red one, the tau rz is minus mu dvz over dr, and dvz over dr here is negative, so this will give me positive tau rz. Okay, so at this point the tau rz is positive, and at this part the tau rz is negative. Okay, so it's interesting, and at the middle the tau rz is 0. Okay, so this is interesting because the tau rz is different, the one is positive and the one is negative. Okay, so that's why when you put, or when you calculate the force acting on the surface of the annulus, you have to remember that the one at kappa r over here, this will have negative. Yeah, put negative here, and the one at r is positive. Yeah, so it's just positive, just like usual. Yeah, but the one here you need to put negative. Okay, okay, I think that's all that I can explain today. I hope that that you can understand that clearly. Any question? Maybe just one question. Maybe just one question. Or if you want to try to absorb this thing, I think that's fine. Yeah, we cannot understand transfer phenomena just by listening once. Yeah, I know, because when I was student, it's difficult as well. Okay, so if you have no questions, we can end this class. And if you sometime, maybe afternoon, evening, think about transfer phenomena, and suddenly you have questions, you can just write the question on the Microsoft Teams chat. Okay. Oh, forget. So I will open the CX now, and then you can fill the CX until 11. Okay. Yeah. Okay. That's all for today. Thank you. See you next time. Bye.